Now, in the simple linear regression analysis, we only included one independent variable in our model. However, in most cases, we want to take into account the effect of many independent variables on our dependent variable. And we want to know the impact of each independent variable on the dependent variable controlling for the other explanatory variables. And we'll see that there are many reasons why we may want to include more explanatory variables in our model, even if we're truly only interested in the effect of one explanatory variable on the dependent variable. And that will be for a later video. In any case, there are many situations when we want to include more than one regressor in our regression model. The way we're going to do that is by expanding the simple linear regression to the multiple linear model. So mathematically, what happens is that the multiple regression model, for example, with two independent variables, x1 and x2, will be written as yi is equal to alpha, the intercept, plus beta1 times x1i plus beta2 times x2i plus ui. So alpha, beta1, and beta2 are parameters, population parameters, that we will want to estimate. And ui is the error term. So the error term basically includes everything that we don't take into account in our formal modeling. So here, whatever the variable y that we take as our dependent variable, we know that there are going to be a lot of variables that affect y, but that we can't include in our model for all kinds of reasons. For instance, maybe we don't have any information about those variables, or they cannot be measured at all, or there's some randomness involved in the determination of yi. So as you can see, it's exactly as for the simple linear regression, except that we added an extra term. And we include the error term again, because we do not expect there to be a perfect linear relationship between x1, x2, and y. So in social sciences, you will never see a relationship that doesn't require an error term. Now, let's have a look at an example. So let us consider the relationship between height, age, and weight among prisoners who are less than 50 years old at the Paisley prison from 1841 to 1883. And as before, we need to assume a direction of causality between the variables. So in this case, we're going to assume that height and age determine weight. Okay, so we're going to assume that the relationship is approximately linear. So I can write that weight for individual I is equal to alpha plus beta1 times height for individual I plus beta2 times age for individual I plus ui. And here in this graph, what I've done is I've put height on one axis, I've put age the other one, and weight on the last axis. And so each point corresponds to one individual. And so we can see that, for example, for this individual, the height will be around 140 and probably around an age of 27, something like that. And really what we're doing when we're doing a multiple linear regression here with two explanatory variables is we're trying to fit a plane through the data, okay? And we'll see how we can model this in a more mathematical way. So remember in the previous case, we had y here, we had x here, and we had some points. So we were in 2 dimensions, and we were trying to fit a line. Here, we're in 3 dimensions, and we're trying to fit a plane through the data. Now, if we had more than 2 explanatory variables, we wouldn't be able to represent it graphically, because obviously we can only represent things up to the 3rd dimension, but it's exactly the same principle. So here, I'm having a linear model with 2 explanatory variables, but it would be exactly the same idea if we wanted to expand it to 3 explanatory variables or more. Now, we assume that the true model for the relationship between height, age, and weight is as follows. But now, how do we estimate the parameters alpha, beta 1, and beta 2? So that is what we'll see in the next video.